Okay, we have one more parametric equations question. This comes from, I think it's the last question from the 2018 paper, or one of the 2018 papers. So one of the tougher papers there is, and last question, so it should be one of the tougher questions on there. Let's see what it's saying. We're given parametric equations, x and y in terms of t. Part A is asking to show all points satisfy, well, this equation. This is a Cartesian equation. Okay, there's no t, it's only x and y. So what we're really being asked to do is convert from parametric form into Cartesian form. Now the way you convert, if you've sort of forgotten, if you have a nice simple equation, so x is 2t and y is t squared, you would just make t the subject in one equation and substitute across. So you would say that t is x over 2, and when you put that into the y equation, so y is t squared, so x over 2 squared, you get a nice Cartesian equation. No t's, only x's and y's. Now this doesn't work when you have trig equations, okay? If you tried this with these trig equations, you would have to write t, I don't know, inverse sine of x minus 3 over 2, and then put that inverse sine in over here. And yes, technically you'd get an equation with no t's, but you'd have cos of 2 of inverse sine, and it's not very neat, and it certainly doesn't look like this. Okay, so when you have trig equations and you're converting from parametric to Cartesian, what you need to do is use an identity. The identity you use is sort of relating to whatever you got. So we've got a sine t and a cos 2t. So you need to think of an identity that uses both of those. So sine t and cos 2t. And we actually know that cos 2t is 1 minus 2 sine squared t. This is an identity. So on both my parametric equations, right, on my x equation, I will rewrite, so sine t is the subject. And on the y equation, I'll rewrite, so cos 2t is the subject. Right, so cos 2t, let's do that one first, is y minus 4 over 2. I've got that from rearranging this equation and making cos 2t the subject. Making sine t the subject over here, that's x minus 3 over 2. Yeah? So 1 minus 2 x minus 3 over 2 squared. Now this equation, it's got no t's, only x's and y's, and it looks like it could, so I'll get to this. So let's deal with this squared term. So x minus 3 squared, and then I have 2 times, there's 1 over 2 squared, so that's 2 over 4, or 1 over 2. I can times top and bottom by 2, sorry, times both sides by 2. Arrive at this equation, and the question asks for y as a subject, y equals, so let's add 4 both sides. And we've got that. Okay, so all points on C do satisfy this equation, we've done that. I guess technically in this question it did tell you the kind of solution. So you could try and substitute in these values of t in, right, and see if it makes a valid identity. But the method I've just shown you will work even if they didn't tell you the curve. Okay, so this is how I would prefer to do it, even if they did not tell you the answer. B says sketch this curve and explain why C does not include all points. Okay, so this is a little weird, right? We've said that, well, these Cartesian equations on the left are the same as these parametric equations. So, these parametric equations are the same as this Cartesian equation. So why is it does not include all points? Well, the parametric equation only involves certain values of t. Okay, and in fact, in this case, even if it involved all values of t, you're going to see in a minute, it still wouldn't be the whole quadratic Cartesian equation. So let's do B here. I'm going to kind of answer kind of II first to help me sketch it. A bit weird. If you look at the expression for x, and you think about the fact that even though t does go between 0 and 2 pi, so we get a full sort of range on all the possible values that sine and cos can take, those still only go between -1 and 1. Right, sine t between -1 and 1. And we do see all those values, as I said. We get every value of t from 0 to 2 pi. So sine t really does take all possible values, yeah, get the whole range. But this means that the biggest value x is going to be is well 3 plus 2 times 1, which is 5. And the smallest value x is going to be is actually, well, 3 plus 2 times minus 1, which is 3 minus 2, or 1. So this is actually the domain of our curve in terms of x. So when I sketch this on, here's x and here's y, I know I have this negative quadratic. I know I've got restricted values of x. Let's figure out what the kind of corresponding values of y are going to be. So if x is 1, I know that, because it's on the curve, y does have to satisfy 6 take away x take away 3 squared. I'll put x equals 1 into there. What you're going to get is 2. And you can check the same thing, actually. When x is 5, y is also going to be 2. Okay. So I've got kind of endpoints of 5, 2 and 1, 2. Now this curve in general, this is, it's got a negative quadratic shape, and it peaks when x is 3 and y is 6. It looks something like this. Because we're restricting the domain between x equals 1 and 5, so between these 2 points, you can kind of add on, it starts at 1, 2, comes up, down, stops here at 5, 2. Okay, and the peak is 3,6. So that's kind of I, and for I'll just mention something about, to explain why it does not include all point. So I'd say that sine t can only go between 1 and negative 1, so x can only go between 1 and 5, which is not all possible values in the real numbers, right? This means any possible number. So we've answered part B. Part C is, I think, why this is so late on the paper. It says the line with equation x plus y equals k intersects this curve at 2 distinct points. State the range of values of k. And what possible values could k be, such that this straight line curve will meet our quadratic curve at 2 points. Okay. First thing I would say is, I said previously that if you want to intersect a Cartesian into a parametric, you should substitute the parametric equations into the Cartesian. So it would look something like x plus y equals k. So you'd say 3 plus 2 sine t plus 4 plus 2 cos 2t equals k. I'm kind of going to break that rule in this question. That's quite a nasty equation to work with, especially when k is unknown. And actually, in this case, we do have a nice Cartesian form. So usually with a parametric, there might not be a very nice Cartesian equation. So you're forced to use a parametric one. So you would do the method I just described, where you sub the parametric equation into your straight line. But the parametric equations actually form a nice, simple Cartesian equation. So we are going to use that for this question. Now, it's asking about the line x plus y equals k. I'm just going to rewrite. So y is negative x plus k. So I can get a bit of a sketch going on. So it's a straight line with gradient negative 1 and y-intercept k. And it's saying that which values of k cause this line to meet the curve twice. Okay, so I can add on to my answer to B here. I don't want to ruin it, so let's say I draw it out again. Okay. So clearly a line something like this is going to go through twice. A line like this is not. A line like this is not. A line like this is not. And this is why it's quite tricky, because if you just answer the question of what happens with the full quadratic equation, it's a bit simpler, but the full equation goes all the way down here, and some lines which would intersect the full equation twice no longer intersect twice now that we've restricted the range, restricted the domain to x being between 1 and 5. Well, you can look at this visually and say, well, which lines do meet twice? Now there's going to be this line here, which goes through this endpoint, is meant to go through, let's just a bit bigger, at 5, 2. And any line actually beneath this will no longer work, right? Only intersects once or 0 times. So this is kind of like one limit. Lines above this are looking pretty good for a little bit, until we get to this tangent line here. Okay, so if I draw that properly, there is a line here, which again is a little bit off, so I'm just going to bring it up, which is tangent to the curve. And any line above this line will no longer intersect it twice. And actually the tangent line doesn't intersect it twice either. But any line in between these two will be good. Okay, any line in between is going to intersect twice. So we can find these values of k for these specific lines. Let's look at that lower bound first. So this will be the value of k for this lower red line here. Now this line goes through the point 5, 2. And I know the equation of the red line was just x plus y equals k. So I can just sub in 5, 2. Right? X plus y equals k was 7. So this red line down here, k was equal to 7. Let's do the upper bound. It's going to be a little bit more tricky. The upper bound is a value of k that makes the red line, let's rewrite it as y equals minus x plus k. It makes this line tangent to the quadratic. The quadratic was y equals 6 minus x minus 3 squared. Okay, so this is now kind of like something you might have seen in year 12, where we're saying we have the straight line, it's tangent to the curve. How do you do that? Well, you sort of solve them simultaneously. So you can sub in negative x plus k here. And we say because the line is tangent to the curve, it only has one solution. And when a quadratic has exactly one solution, we can use a discriminant. Okay, so maybe it's sort of like ringing a few bells here. Let's expand this all out. So that's going to be negative x squared. This will be plus, so this will be negative 6x, so plus 6x, and that'll be plus 9, so take away 9. Has only one solution. X squared, let's add it all over. Take away 7x. That's negative 3 here, so plus k. Take away 3 has only one solution. So equals 0, has only one solution. So we can use the fact that the discriminant is equal to 0. So that's negative 7 squared. Take away 4, lots of a is 1. C is k, take away 3 equals 0. Okay, 49. Take away 4 bracket k minus 3, 0. Let's solve for k. For k minus 3 is going to be 49 over 4. Let's add 3. So 49 over 4 plus 3 is 61. 4. This is not right. I've just done something silly probably. Yeah, this should be plus 3 here. Sorry if you're screaming at the camera or screaming at you. Doing over there. This would be k plus 3. K plus 3 plus 3 plus 3. So k should be 49 over 4. Take away 3, which will give me 37 over 4. That's the correct solution. Okay. So as long as you can do some basic algebra, you'll be fine. So this line was k equals 37 over 4. Yeah. To put my final answer kind of together, right, which values of k, in set notation by the way, make this work? 2 distinct solutions, it says. So 2 distinct points means different points, so 2 different solutions. So actually, the value k equals 7 works, because when k is 7, I do get 2 solutions. Right? There's a solution here, and there's a solution 5, 2. When k equals 37 over 4, that's only one solution. Okay. For 2 distinct solutions, we would actually be interested in b squared minus 4ac greater than 0. Right? That would give us any value of k which is strictly less than 37 over 4. Okay, so I'm not including 37 over 4 because this line only has one solution. But I mean, this by the way, this is about, if you divide it, 9.25. So any kind of value of k in between will be a line in between, and all of those will work. So there's my final answer. I guess I do have to write set notation, so let's do that. The set of k, there can be any real number, such that 7 is less than to k is less than 57/4, and that will be the final answer for part C. So I hope that helps. You could have tried this different ways. This, I think, is probably the quickest and easiest way to see it. Let me know if you do have any different strategies, and if you got them to work, or maybe if it didn't work and you want to ask a question. So yeah, I could help with that in the comments. And good luck with your revision. Your exams are soon.